So hello and welcome to day 8 of our coding mastery graph mastery series. Today's question is Leetcode 924, which is minimize malware spread. This is marked hard on Leetcode, and I think it is like not very hard, but it is a good question. Like it can be called a good question on Leetcode. It's like upper medium type, so maybe even hard, I don't know. So yeah, Leetcode 924. Let's go day 8 of graph mastery series. So let's start with introduction. What my series is. Basically, all the sheets or whatever playlist you are following, it takes you from a 0 to beginner level. And like they will, I hope you know all the formulas, like all the basic codes and all the like mugging up part. I hope you know the syntax, so and basic code structure. So there are numerous playlists available to take you till here, but from here I am taking you to the mastery level, which is not available anywhere that freely, I noticed. And yeah, so I think that you need to have mastery in harder topics like graphs, because the companies have adapted themselves and they also ask good questions on graph, not from the classic SD sheet of Striver or any sheet, but I think they ask lesser common questions and harder questions. So today's question is Leetcode 924, minimize malware spread. I hope you have read the question once and attempted the question for 10 minutes without use of any AI or any tool of help, so that you get the thorough idea of question and everything. Still, let me give you an introduction. Today is date of graph mastery series. So introduction is that we are given a matrix, index 0 and 2 we are assuming, and wherever there is a 1, instead of the index which is itself, wherever there is a 1, then that means that the indexes are connected, like computer 0 and computer 1 are connected in this case, and we are ignoring the index with same value, like 2 2 1 1, and these are not really taken into consideration. And similarly, 1 0 here signifies 1, means 1 and 0 are connected, and 2 is not connected to anybody except for itself, which is an obvious. So ultimately our network looks like this: computer 0, computer 1, and computer 2. Now we are also given a set initial, which is telling you that these many nodes, like wherever the number of nodes in vector are initially infected by malware, like let's say if the initial have 0 as as a value, then that means this whole network is infected. Let's say we also have 2, then that means this network is also infected. And since we have 0 also, so this network is also infected. Now we are supposed to answer, we are allowed to remove one and exactly one node from this initial. Basically, we need to remove virus from any one of them, such that the the largest number of computer gets virus disinfected. Like if we remove 2, then how many computers get free from virus? Only 1, because there's only 1 in this network. But if we remove 0, then this whole network of 0 and 1 will get disinfected from virus, and hence this is a better removal. 0 is a better removal. So we need to remove the best removal, like the best value from this initial set, such that the removal of that value would give us the maximum value of non-infected computer. So this is the question. And okay, so let me give you an intuition. Obviously, this should seem like a DSU question to you, because there are connections, and you notice that there are computers in groups, and even one infection causes infection to the whole group. So intuition should be clear that it is a DSU question, because connectivity is involved, graphs is obviously involved, and yeah, and there are connected and disconnected components, and we have to operate individually on all the components. So that's why this is a DSU question. Okay, now we are running towards the strategy part. These 3, 4, and 5, these steps are the most major steps to help you solve the question, like help you build strategy for the question. Let's take an example. Let's say we are given a network like this. This will be given in matrix format, as I mentioned earlier, but this can be converted to this by you easily, I suppose. Like matrix can be converted to adjacency list, right? I am marking with red wherever there is an infection. Let's say this node is infected, node 2 is infected, and node 5 and 7 both are infected. Okay, so that means the initial vector as mentioned in question is 257. 2 is infected, 5 is infected, 7 is infected. Now let's say we remove, just a second. Let's say we remove the virus from 2. Then this network is saved. Currently this network is under the virus infection, but if we remove 2, then this network is saved from it. So after removing 2, our current max number of computers we can save is 3 because there are 3 computers connected in it. Let's consider 5. So if we remove the virus from 5, what happens? Does this whole component become free from the virus? Does this whole component becomes free from the virus? No, because 7 still has the virus and we are only allowed to remove one of the component. So even if we remove 5, these 4 components are still under the virus because we have a node which is under the influence of virus. So even after removing 5, we have our value 0. And note that we can only remove one node, so we cannot remove 7, hence this component will be obviously affected. Let's say if we remove 7, just let me rebuild this here in a rough way. This is infected and this is infected. Now let's say we remove 7. If we remove the virus from 7, then does this network become free from the virus? No, because we still have 5 as a node which is still a virus to this network. As we know that any one node having the virus will like the whole component gets infected with virus. Hence removing 7 won't work. So clearly one thing which we can take from here is that that whenever a component has more than one infected part, more than one infected node, whenever a component has more than one infected node, then that means all the any removal won't work. Like even if we remove 5, then 7 will make this network corrupt. If we remove 7, then 5 will make this network corrupt. So even if one of the node has the virus, then the whole network will be corrupt. So there's no point in removing 5 because we get 0 value from it. And even from 0, we get 0 value from it because no computers are saved from virus. But in this case, as you saw, this is the only virus, this is the only computer with virus and it gets saved from, the whole component gets saved. So whenever a component has more than one infected node, all infected nodes in that are useless because removing, as mentioned earlier, there are no benefit in removing any one of the node. All infected nodes are useless to remove. So clearly these are not our answer. Secondly, let me give you another example for this. Let's build here quickly. The nodes marked in yellow are infected. And these are the components. Again, it will be given in matrix form, but I think you would be able to convert it to this form using DSU. That is something which is a prerequisite. I will help you in that when I show you the code, but you should know how to construct the DSU class or how to use DSU functions and all. That is a prerequisite. Anyway, so we have these 4 components. After we have unioned them accordingly, and after that we get these 4 components, out of which these are the infected ones. And how are we unioning them? We are unioning them using DSU, again a prerequisite. So once we have unioned them, and finally from the initial set we have these as the infected value. What would be our best answer? Obviously utilizing 0.1, this is straight up rejected. So these this can't be our answer, neither can this be our answer, because removing this won't be any benefit to us. Okay, now we have 3 options, this or this. Now what do you think is our best answer? If we free this computer from virus, how many other computers are saved? 3. Total we have 3 computers which are free from virus after we remove virus from this. In this case, if we remove this node from virus, how many computers do we get free from virus? That is 2. Because there are two computers currently in the influence of virus, but removing this would save it from it. Similarly, in this case, if we remove this, how many computers get saved from the virus? Obviously 4. Before removing, there are 4 computers which are directly connected by virus. You should have read the question properly, then you would know, you would understand this part. There are 4 components directly connected by virus, and if we remove it, then we save all the 4 computers. So obviously our answer is this node. Okay, so let me ask you, how would you know the component size? Obviously, yeah, let me write the second point. Second point is our best answer is, what is best answer? Our answer is to remove node with largest component size. Again, components and all this is a DSU part, which you should know. So our best answer is to remove the largest component size, like the node with the largest component size, infected node with the largest component size. Obviously, infected node only we are removing. So our answer, obviously, it should follow the first point, which is the connection should not have more than one infected node. And second point is our answer will be to remove the node with the largest component size. Now, let me ask you a question. How do you know the largest component size? Which node has how do you know the component size of current node? How do you figure out what is the component size of a given node? See, different people learn DSU in different ways. So I will follow, I've used a class of DSU and then I create a size vector there. And if someone else uses DSU using struct or using functions, then also they must have a replacement for it, suitable replacement for it. So in my case, I have a size vector there, and what does it store? It stores the size of the components. Okay, but there's a problem. Just think about it. What is the problem? The problem is that the size vector doesn't have updated value. Let's say this is 3 and this is 2. This is 4, let's say. Okay. Now, when union you are doing, this gets connected to this. But the size of this node, like the parent node of this component is updated, but this node's parent is not updated. So this would store 3 only as the latest, like even after unioning, the current answer is 1, 2, 3, 4, 5, 6, 7, but it would still have 3 because we don't update the size vector of the, the child node, we only update the size vector of the new node, like the node which is added to it, and then we update the size of the parent of the whole connected component. So how do we get the size of the component? Obviously not the individual node, but we find the parent of the node. Again, DSU, find parent, and then use the size. Now the size vector stores correct value for the parent. For the parent, it is all updated values because let's say the parents has changed and new parent is this. So this would get updated to all this node, like 4 already, and it would also get added 3 to it. So this would have 7, which is correct. So instead of directly searching for the size using the given node, we search for the size using the parent node. Okay. I hope you understood it. Let me just make you understand again clearly. All that is a prerequisite part, but I will try to get it cleared within your head if anyone has confusion. We are unioning these 2 nodes, okay, this node and this node. And the current size of this node is 3 and current size of this node is 5. So if you know DSU, then this would get connected here. And the size of this parent of this node, let's say this is the parent, size of parents of this node is added to the size of the new node. So the new would be 5 plus 3 is equal to 8. So the updated value of this node is stored here, but there is no updation for this node. Okay, this remains 3 only. So to get the correct node size of a given node, correct component size of a given node, we need to find the parent of it using find parent method when you are constructing the DSU class. So using the find parent method, we find the parent node, and then using the size array, which stores the correct value for the parent node, not for the node. It is not updated for the node, but for the parent, it stores the correct value of the component. And using that, we get the component size. And obviously, we need the max component size for maximum computers to be saved. As explained here, we need to get the maximum component size, and that way we can have our second point achieved and we will get our question. This is the only requirement of the question. Firstly, find the useless nodes, which is component which having more than 2 infected nodes. Those are the useless nodes. There is no profit in removing these two. And secondly, then we are only left with the components which have only one infected node, and then we using, as all the things mentioned here, using the parent and then getting the size, we track the maximum, and hence we track the best solution to our answer. Okay, I hope you got it. Let me give you what's the next step. Okay, so we have done this part. I think dry run is also done. Okay, let me do the dry run one time. For one last time, I will tell you what our final strategy is. This is a raw version of what we are going to do. But our final strategy would be like this. Let's say we have unioned all our things. I hope you get how we are getting the different components. Let me give you an example for that also. Let's say we have 1 1 1 1 1 1 1 0 0 0 1 2 0 1 2. So if this is given, obviously same node values are ignored, but this 0 and 1 is connected, so that means 0 and 1 is connected, and we would union 0 and 1 here. Okay, so when we union 0 and 1, they will get connected to it. Now again, union is a DSU part, DSU prerequisite. Whenever we find a 1, we union them. Okay, whenever we find a 1 and the index I and j are not equal, we union them. So we iterate through the graph, and whenever we find I not equal to j, and like graph, let's say grid of ij is equal to 1, so we union ds.union by size I and j. So that way 0 and 1 would be union, and hence we will get our graph like this. Now let's get back to a complex example. Let's say we have built this graph. And then let me mark infected by yellow. Okay, so let's say this is infected, this is infected, and this is infected, and this is also infected. Okay, so firstly, as I explained you till now, this cannot be our answer, but how to implement it? Because this has 2 infected nodes, this component. So how do we implement it? We implement it using, like we would traverse all the components, and whenever we find, we can keep a map. Okay, we can keep a map of parent, and you know this parent basically is the identification of each component. Each component has one and only one parent, and each parent is unique. So we find for each node we will traverse, for each infected node we will check its parents and increase the size, like increase the count of the parents infected node. I will explain you in a better way inside the code. Let me give you an example. Let's say this is an infected node. We will traverse the infected array we are traversing. Okay, so this is the infected node. We find its parent. Let's say this is node 0. This one is node 0. Parent is 0, so we do m of 0 plus plus. So map has a 0 value of 1. Then again we traverse the infected array. Obviously it is a linear traversal since we are given an array. There is no BFS or DFS involved. Don't get confused by seeing the figures. We get to this part. Okay, now this is node 0. Its parent would be found, and its parent is itself, which is node 0. So we would update the value of it, m of 0 plus plus. We will do again. Then again next traversal we will do, let's say this is node 1, and we would find its parent. Whatever parent we are getting, we would increase the value. Similarly, next we will find this node and we will find its parents and we will increase its own value. So 2, and let's say this is node 2. Now we will traverse the map, okay, and whichever has the value greater than equal to 2. What does it mean? It means that this component has more than 2 infected nodes. Whenever the map has a greater value than 2, that means this component has a more than 2 infected nodes. So the parent will be added to useless removal set. Useless removal set we would maintain. This would represent that we are not supposed to remove anything from here because there is literally zero profit, no benefit in removing this, because the other infected node would still infect the whole component. So yeah, let me give you a brief overview of this step again. We would for each infected node, let's say we are given 0, 1, 2, 3. Let me rename this node and let's say this is node 3. So 0 and 3 are in the same component. For each, this is given to you. This is the initial array given to you. These are initially infected. So for each of the array, we will find its parents, and it would do a plus plus to their parent. So let's say 0's parent is 0 itself. So we will increase its value in the map m of 0 plus plus. Then we will find, similarly for 1, we will find its parent and increase its value. For 2, we will find its parents and increase its value. For 3, we will again find its parents and it will come out to be 0. This is again DSU. Yeah, obviously this is a prerequisite, you must have understood by now. So again we will do m of 0 plus plus and this would become 2. Now map will have 0 key and value as 2. That means the component with the head as 0, has 2 infected nodes. So obviously this component is useless. So we won't use this component, okay? And we would add it in a set. Set would have all the integer with the useless connections. So that way we can have our useless connection sorted. Okay, and then what we will do is, so our useless connection is sorted, okay? Next step is to again traverse the initial array. What was it? 0, 1, 2, 3. And as mentioned above, what we are supposed to do is we firstly check if the parent of the current node is in useless removal or not. So 0's parent comes out to be 0 as seen in the above example. So we will simply continue. There's no usage in removing 0. Then we will go to 1. We will again check, is this in useless removal set? Is there any benefit in removing this node? It won't, because the map value was only 1 and we only add it to the useless removal set if map value of the parent is 2. So this isn't, okay? So we'll continue our check. Now what I told you, we'll firstly find its parent, which will, let's say, come out to be 1 again. And then from the size array provided by the DSU class, from the size array using the DSU class, we'll get its component size, which will come out to be, how much will it come out to be? Let me see. 1 has 3 size. Okay, 1 has 3 size, you can see. So it will come out to be 3. And our answer will be updated to 1 because our node is 1. And current is 3 because current best size is 3 we have got. Then we will again go to the next one, which is 2. Now for 2 we will again check the size. What will be this? We will check for 2's parents firstly, which will come out to be 2 or whatever, some node from this parent. Sorry, some parent from this node, like either this node will come or this node will come. It depends on the implementation of DSU. Then we will check for useless removal. Will it be in useless removal? No, because it has only 1 infected node in its component. Okay. Now we'll check for size of its parent using the size function. It will come out to be 2. Is it better than current value? No, we only have a value which saves 3 computers from getting infected. So we won't update answer or current. Now we'll go to 3. We will find its parent. 3's parent is 0. Is it in useless removal? Is it in useless removal? Yes, it is, because the map's value of its parent was 2. That means it has 2 infected nodes in its connection, and removing either of them won't save the whole component from getting infected, as the other infected node would infect the whole connection either way. And we are only supposed to remove one node, so there's no point in removing this. So it won't have any iteration. So our final answer comes out to be 1. And this correct value tells us how many computer it saves. Although it doesn't ask that it saves 3 computer, but our final answer comes out to be 1, as 1 is the ultimate answer. Like removing 1 from the virus list gets us saves us 3 computer. So as you can see, if we get this one free from virus, we would have our whole component free from virus, and which is 3, which is the maximum number of computer we can save. Finally, let me see what we are supposed to do. Here we are supposed to write the algorithm. I hope I have written it and I have explained you enough. Okay, I will write still for the sake of completing the video. Written algorithm. I hope you try this question without seeing the code. Like you can try this question from here on, pause the video and go attempt the question. So what is the written algorithm is firstly check for useless removal. Now how to check for useless removal, I'm not going deep into it again. Obviously the map thing, you need to check that not more than 2 of the nodes are infected inside the map. So check for useless removal, then traverse the array, traverse the initial array, initially infected array, and then inside the traversal what you're supposed to do is if useless removal, then continue, like there's no point in removing this, else you need to get the size of its component. Get the size of its component. How you are supposed to do it, you are supposed to find the parent and then check for using ds.size array, you need to check the size. And then if size is greater than the current, that means you can save like more computers than the current answer, whatever you are showing. So update current. Let's say currently you were saying 3 computers and now you can save 4 computers. Here you were saying 3 computers till now. Till now current was 3, that means 3 computers were being saved, but now the new value gets us 4. So 4 computers is a better option. So update current. Now current gets 4. And obviously update the answer. Answer gets the value of current node, like whatever node value we are traversing in the initial array. Finally return answer. Let me give you the code to it. I've already done this question. This is the DSU structure. This is the DSU class which I have already explained many times. And it is also a prerequisite. Note here is the size array which keeps track of the size of the current component. Okay, and yeah, you can notice here that whenever we add a component, the value of the new parent gets updated. The value of the new parent gets updated and the old parent doesn't updated, as size of PB is not updated. So this was all for the DSU class. Rest is prerequisite. Here also the one with the like only the parent is updated, new parent is updated, old parent's value of size is not updated. Size is an array, so the size of the parent array is updated. Okay, like in the size array, the new parent's value gets updated to the total component size. Okay, so we need to check for the parents. I hope you get this point. This is a very important point. We can't directly check for, if we need to check for a node, we firstly need to find its parent and then we need to find its size, because size of PB is not updated, although it is connected to a bigger component. But size of P is updated. Okay. Now let me take you to the code. This is the DSU class ending here. Now this is the main code. We get the graph size and we call the DSU class. Then, as mentioned, we are building from the matrix, we are unioning the, ignore the same index values, and whenever there's a 1 in the graph, then we union them, because that means they are connected to the same network. As I hope you understood this part. That means I and j is equal to 1 means I and j belongs to same network. So that's why we are unioning them. Then we get the size. This is for the useless removal part. We get the map. and for traverse the initial array, and when we find like we get the parents and we update the map to plus plus, and if the map size is 2, that means, as I have already explained, that means that this node, like this node is no value to remove, it would give no value to remove, so we added two useless removals. Then we sort, this is something I missed, we sort the initial array because there's a small condition in the question that we are, if 2 value gives same, like same number of computers are saved from 2 value, then we are supposed to return the smaller value. That's why I've solved it, so we encounter the smaller value first. Then again we start with the initial 0, this is a start, like we can initialize it with anything, initial 0 is okay, and current computer saved is 0. Then we traverse the initial array again, as mentioned, we find its parent, and if it is in useless removals, that means if it is a part of network which already has more than one infected node, then there's no point in removing it because the other node would still infect the whole component. So if it is a part of component having more than two infected nodes, then there's no point in having this. So we continue from here only, check for the next answer. But if it is not, then we continue. We get the profit using parent again. As I mentioned, the parent has the updated value of the component size, not every node in the component has that thing. So the parent of that profit, we get the size of the component using ds.size. This is again DSU, and profit is a variable which we maintain that how many computers is saved. Profit basically tells computers saved using this. So let's call it computer saved. And if computer saved is better than the current number of computers we can save, then we update the value to the new computers saved. This is again a basic part, that's why I'm not putting a lot of effort in it, but yeah, overall it is that we check the value how many computers we are saving, and then if the current number of value is, like if it is a better option to save this many computers, then we update the answer like this node is better option, and we update the current value also, like this many computers are a better option, so now this is our current, and then finally we return answer. Let's run this should work. Okay, ignore the typos. Let's submit it. As you can see, this is accepted. Let's move on to the time complexity, which is the final part of the video. Obviously, we are traversing whole of the graph, so it is n square, and DSU is time complexity of using DSU is 4 alpha due to path compression and other efficient methods, which is almost equal to constant, so we don't consider it. One thing we are doing is we are inserting in map and set, so this is n log n, but n is where n is the size of array, but still I think it is less than the size of graph, so n square is the dominant term, and that would be our answer. Ideally our answer should be dominant term out of m log m and n square, where m is size of initial array and n is size of the grid given to us, and space complexity is O of n. Thanks for watching.